Hi everyone, thank you for joining. So this is the third video on Einstein's special theory of relativity. In the last video, we talked about Galilean principle of relativity, and the conclusion was that the Newton's law of motion are valid in all inertial reference frames. But to ensure that we understand what does this inertial reference frame mean, so let's be specific. So first of all, let me write it down. What is a reference frame? Well, the reference frame is a coordinate system. It's a coordinate system in which an experimenter makes position and time measurements. Position and time measurements. This word measurements becomes more exciting if you're dealing with quantum mechanics, but we're taking it as a very simple word as measurement in classical and Einstein's physics. So it's a measurement of physical events. So yeah, that's the definition of a reference frame. So a coordinate system in which an experiment makes a position and time measurement of a physical event, right? Or events. Okay, so that's what the reference frame is. Now, what is inertial reference frame? Well, inertial reference frame has if we understand what a reference frame is, inertial reference frame is simply that when we're looking at a reference frame that moves with, I'll write it down just to ensure. So inertial reference frame. What is it? Well, it's a reference frame, and it's a reference frame that moves with constant speed. It moves with constant speed in a straight line. Okay, that's what the inertial reference frame is. Now, why is it important? Well, it's important because we've discussed in the previous video that the Newton's laws are valid in these reference frames. In other words, in inertial reference frames, right? Just a quick recap. We had a vector equation. Looking at the diagram of the two observers, we had r is equal to r dashed plus r. If this motion is taking place along the x direction, you have x is equal to x dashed plus. Now, instead of r, we can write the velocity v, which you can see here. So that's v along the x direction, let's say, and multiplied by time. Why is that? Because we're assuming a r, the capital R, to we're assuming one observer to move at a constant velocity with respect to another observer. So we're using this very simple and basic GCSE formula. And if two observers were approaching one another, we would just have minus rather than plus. That serves the same thing. Okay, so right. So why is this important? Well, if we know where and when an event occurred in one reference frame, we can transform that position into any other reference frame that moves relative to the first with constant velocity v. That's why it is important. Now, so let's consider a very basic projectile motion. So let's draw our axis. Let it be x-axis. And let's say that we have someone throwing an object, a ball or something, at 22 meters per second at 63 degrees. Okay, these numbers are picked specially, so that it turns out to be the horizontal and the vertical components turns out to be nice numbers. Okay, so we have this parabolic motion. It's the floor. Okay, so yeah, so what we're trying to, our aim here is to understand this relation better. So let's gather some information. So what is this horizontal? What is the horizontal distance traveled by the subject from there to there? Okay, let's find that. Now, how are we going to find that? Well, horizontally, assuming there is no resistance, we're just looking at the speed distance time relation. So we use the vertical component and to work out the time, and we use that time to solve the horizontal equation. So we have S. This is vertically. Now, right, well, what is S? S is the displacement. If you're considering the whole journey, displacement is 0. So it starts from at point A and to B. They are at the same level horizontally, so the height is 0, therefore displacement vertically is 0. That's equal to ut. Now, what is u? U is 22 sine 63. So if we say u is 22, that means we've already taken acceleration to be negative. So that is 9.8. So minus half t squared. So I'm using s is equal to ut plus half a t squared. Okay, we can use this because acceleration is constant. We're assuming acceleration to be constant, yeah? Okay, so that means we have t, well, 22 sine 63 turns out to be 19.6 minus 4.9 t, which is equal to 0. That implies t is 0. Yep, so the height was 0 to begin with, so that makes sense. Or t will equal to 4, so it's 4 seconds. It takes 4 seconds for this object to move from A to B, and if you look at the horizontally, x is equal to distance is speed times time, so it's 4 times 22 cos 63, which turns out to be 4 times 10, which is 40 meters. Now, this is not a video on projectiles. The only reason we're doing this because we want to now make this more interesting by bringing in, let me shift everything down. Let's say now we have a cyclist at point A, and this person is traveling at a speed, let's say in that direction, 10 meters per second. Yeah. Now, how would this motion appear to be to, let me call this point C here, C for cyclist. So what will he observe? Well, if you think about it, what is the horizontal velocity of this particle, this object? Well, 22 cos 63, which turns out to be 10 meters per second. Okay, which is equivalent to the speed of the cyclist. So what will the cyclist see? Well, if we move this down here, let me move it down further. So let's draw another line. That's for cyclist. This is x, right? Well, according to cyclist, let's see that at time t is equal to 4, cyclist is here. Yeah. So what will he observe is that he will observe that, in other words, the ball is going up and down vertically only. Not there will be no horizontal motion according to the cyclist. So the person who throw the ball will be here, which would be at minus 40 meters. If you remember, that was 40 meters. Yeah. So let me redraw this because it looks like as if it is moving. It's not moving. So according to the cyclist who is here, the ball will be just performing vertical motion. It will be going up and down. You know, this will be t is equal to 0. I should write t is equal to 4 there. So that's what the person will be observing. Now, is this consistent with Galilean transformation? Well, let's think about it. Let's go back to this formula here. So it is saying x is equal to x dashed plus vxt. Now, so this is, if we rearrange it, the position observed by the cyclist, I'm going to call this c, is equal to x minus vxt. Now, what is vx? Do you remember that we said this has nothing to do with the object? It is the velocity of one observer relative to the other observer. So, well, what is x? What is the horizontal component of the position? Well, it will simply be, x will simply be velocity times time, isn't it? We're looking at horizontally. There is no acceleration, so this will be 10t. Why 10t? Because 22 cos 63 will be 10, and that is the horizontal motion observed by the observer at A. And then we want to say it's minus Vx times t. But what is Vx? What is the relative motion of between the cyclist and the person at A? Well, according to cyclist, the person at A will be going back at 10 meters per second. So in other words, what we will have is 10 times t, you get 0. So in short, the position of the projectile with respect to the cyclist is just 0, horizontal position. In other words, horizontally, this ball is not moving with respect to the cyclist. Yeah. So we see the consistency with our intuition and Galilean the transformation, Galilean transformation. So there's a consistency. One more point I'd like to make is that if you remember, if we do derivation here, so if we differentiate, we have velocity is equal to v dashed. I'm going to call this c and this is a, plus dr dt. Okay, so in other words, this boils down to dr dt is simply velocity in the x direction of the relative velocity of the observers. And if we rearrange that, what do we get? We get vc, v dashed c is equal to velocity a minus capital V, right? So, right, now let's see if this is consistent. Well, let's think about it. So, what is that? Well, we don't know what that is we want to find, but what is VA? Well, VA is simply the velocity, horizontal velocity, observed of the object observed by the observer at A, so that's simply 10 meters per second. And what is the relative velocity of the two reference frames? Well, that's also 10 meters per second. Yeah, so that's equal to 0 again. In other words, what we've seen here, the position doesn't change. Not only the position doesn't change, but the velocity as well. So with respect to the cyclist, the velocity, horizontal velocity of the ball is equal to 0. So ball appears to be stationary to the cyclist. Yeah. So this was a sort of short video to show that there is no inconsistency with our intuition and Galilean principle of relativity and Galilean transformation of position and velocity. Now, why is this important? Well, it's important because that this makes intuitive sense. But when Einstein comes in, he will tell us we need to think a bit more careful about our intuition. Yeah, okay, right. So in the next video, I think we will start looking at the Einstein's contribution to this. Identifying the problem and solving the problem. Okay. Well, I hope you enjoyed it. I hope you found it inspiring. Thank you for joining, and I look forward to seeing you in my next video. Thank you.